Welcome to the course on plasma physics and applications. Today, in our last lecture, we will complete the discussion of thermonuclear fusion. We will try to address the questions of what are the last steps of research and development that are needed to produce electricity from fusion, and how do we close the gaps in our knowledge and connect what we do today on the present experiments to ITER and DEMO. I remind you that ITER will be the machine that will demonstrate the scientific and technological feasibility of fusion on Earth, while DEMO will be the ultimate step, that is the step that will demonstrate that fusion power can be deployed commercially. To begin our discussion, I'd like to remind ourselves of the progress in magnetic confinement fusion, represented in this slide in terms of the so-called fusion triple product, that is the product of the density of the fuel of the plasma, that is the ions, the confinement time for the energy, and the temperature of the ions. This triple product is represented as a function of the central ion temperature in kilo-electron-volt. The different points correspond to different experiments around the world. In fact, by far, not all of the experiments are represented in this chart. Nevertheless, we get a feeling that from the early 70s to the 80s and to the 90s, we have made terrific progress towards the reactor condition that we need to achieve in order for the plasma to actually produce energy. We notice that the white points here correspond to the actual full deuterium tritium experiments performed at TFTR in Princeton, US, and at JET in England. These points, in fact, don't correspond necessarily to the best triple product we can achieve. I think the record today still remains with the JT60 upgrade machine in Japan. We're still a little bit far from what we need to achieve, that is a fusion gain of about 10 in ITER, and a step beyond that, there will be the demonstration for an actual reactor to work, which will require a fusion gain of the order of, say, 30 to 40, not necessarily to ignition, as we have seen in previous lectures. Different parts of the world, different countries, have defined or are defining their strategies to get to fusion power. The different approaches are often complementary, but also reflect the degree of urgency that's perceived in the different parts of the world for a new energy source that's compatible with sustainable development. Being in Europe myself and the whole staff of this course, we will base the lecture on a roadmap that we have developed in Europe, which I think is a good example of a combination of pragmatism and ambition. The European roadmap aims at producing fusion electricity by 2050. This requires the construction of DEMO around 2030. It also requires an early involvement in industry and, of course, international collaboration beyond the borders of Europe. I'd like to say a few words about the main missions into which the European roadmap to fusion power is structured, without the pretension of being exhausting in this description. There are several missions that have to do with fusion technology, and other missions that have to do with, say, more plasma physics related problems. Let's go through the missions. The first mission is to optimize the operation of the plasma. We can have two approaches: the inductive operation of a tokamak, in which the current is driven primarily by the transformer action, and the possible steady-state regime of operation in which the current may be driven primarily not by the ohmic transformer but by external sources of momentum and by the intrinsic source of current in the plasma due to its own profiles. So we need to understand how we can optimize these scenarios in order to get to the conditions for a reactor. We also need to address the question of the heat exhaust, as we have discussed in previous lectures, both in what we call the baseline configuration, that is what we have in our hands today, and in configurations that are more advanced with possible innovative solutions that we are exploring in parallel with the baseline. We need to address the question of materials, how we cope with the very large neutron irradiation, in particular from the tokamak plasma. We need to worry about how, in practice, we can breed tritium. We have discussed the principles behind the idea of breeding tritium in a blanket, but we need to test different concepts for the blanket. There will be tests in ITER, but it will also be tests in parallel. An important element of fusion is, of course, the safety of it. The fusion technology can be completely safe, but we need to really demonstrate all the details of this particular feature. We need to get to demo. As I said before, in the European view, we need to get to demo construction around 2030 in order for demo to operate and tell us what the conditions are in which we can deploy fusion power commercially. So we need to concentrate already now on trying to identify what the best concept for demo can be. Another point that in the European roadmap is highlighted as really a mission is to keep the cost of electricity for fusion relatively low. The idea here is that if we go on a path that leads us to gigantic experiments and unsustainable costs for fusion reactors, that path will not lead to the real deployment of fusion as a commercial energy source. So we need to keep that in mind. And finally, last but not least, we have the line of the stellarator. This is not the main line in a roadmap, which is based primarily on tokamaks, but it's a line that can provide some sort of insurance policy against possible problems from the tokamak line. Stellarator machines may be a generator behind in terms of readiness for the achievement of the conditions for fusion, but they have, as discussed in previous lectures, quite interesting potential advantages over tokamaks. In fact, the largest stellarator ever built will become operational this very year in Germany. That's Wennerstein 7X. So how do we connect the different devices and their findings on the way to ITER? One way to look at that is the so-called step-ladder approach that we have taken in Europe. I represent here the three machines that are of similar shape. ASDEX upgrade in Germany, the JET European device in England, and ITER. And you can notice the difference between the machine is really primarily the size. So extrapolations from ASDEX to JET are relatively easy, as should be relatively easy to extrapolate from JET to ITER, because the number of conditions are kept similar. In particular, we noticed that ASDEX upgrade, which we'll discuss a little bit more in detail, as we will for JET, has a full metal wall now. JET has a combination of tungsten and beryllium, as is foreseen for ITER. So there will be also the possibility of investigating the problem of having some kind of materials facing the plasma that will be the same as in ITER. The sizes are more or less in scale here. As you also notice that there is a number of megajoule represented here. That's the energy content of the plasma, going from 1 megajoule for ASDEX to 20 for JET and to about 350 for ITER. Now, in addition to really having this step ladder that provides similar devices with just very different sizes, we also in Europe contemplating using other experiments that explore approaches that are alternative to these machines belonging to the step ladder approach, if you like. For example, alternatives in the sense that we can explore innovative ways of addressing the plasma exhaust problem. And these devices that are at the moment present in the European program are the MAS device, which is a spherical tokamak in Calais, UK, and the TCV device, which is a tokamak of variable shapes, which is in Lausanne, Switzerland. It's also important to have different kinds of devices so that validation of numerical models and codes can be done on a variety of scales and a variety of conditions. The combination of these smaller tokamaks, smaller than JET that is referred to in Europe as the medium-sized tokamaks, and that's an important part of our roadmap. Again, these medium-sized tokamaks at present are three. ASDEX upgrade in Germany, which has a major radius of about 1.6 meters, minor radius up to 80 centimeters, slightly less than 4 Tesla for magnetic field, and up to 2 megaamperes of plasma current. The mass spherical tokamak in UK is significantly smaller. It's 85 centimeters of major radius, 65 of minor radius. Immediately notice how close the two values are, and that's why we refer to as spherical tokamak. For the moment, the magnetic field has been limited to about half a Tesla, but as I say, in a moment there will be significant upgrades to that, and the current is up to almost 1.5 megaamperes. In the tokamak TCV, we have a similar size to mast in terms of major radius, but a conventional aspect ratio, which implies a much smaller minor radius, A of about 25 centimeters, with a very elongated cross-section. Field is also up to about 1.44 or 1.5 Tesla, and about megaampere of maximum plasma current. So these medium-sized tokamaks in Europe are foreseen to, as we see in the roadmap here, to provide input for the physics and the technology, even of the steady-state approach to plasma operation. They also are very important in exploring the question of the heat exhaust, in particular by pushing advanced configurations that are not possible on JET. I'd like to say a few words about the individual devices. First, ASDEX upgrade, which is the largest of the three, and it's also the one that has the most complete set of heating systems. It has the ion cyclotron resonance heating up to 8 megawatts in a range 30 to 60 megahertz, which is the same range as actually as in JET and in ITER. It has the electron cyclotron resonance heating system up to 6 megawatts, about 140 gigahertz of frequency, and a neutron beam injection, 20 megawatts at energies up to 100 kiloelectron volt, with the possibility of injecting beams tangentially, that is to also drive non-inductive current by the beams. Among the interesting ancillaries to ASDEX, in addition to very large and complete set of diagnostics, there is the injection of pellets. This is a way to fuel the core of the plasma in addition to what the neutron beam can provide. And it's a system that is specifically designed in order for the pellets to reach more effectively the very center of the plasma. Exhaust studies are possible on ASDEX at very high ratio of the power over the major radius, which is an important figure of merit, because the power will be concentrated in a thin layer around the diverter, and we need for ITER and for theory for demo to really reach very high values of this ratio. There will be also the possibility of studying the limit on beta with the heating systems that now are implemented, and to use electron cyclotron current drive for control of MHD instabilities. ASDEX upgrade has also internal coils for the control of edge instabilities. As we have discussed in other lectures, the plasma at the edge develops very, very strong gradients, which can in turn give rise to very violent instabilities called edge localized modes or ELMs, which can throw out on a very short time scale a lot of energy and particles, and that may be damaging the first wall. So this is something to be either avoid or mitigate. And the use of coils such as those represented here can help in mitigating these instabilities. But conditions in which this method can work, both for ITER and potentially even for demo, need to be understood. Now we said MAST is a spherical tokamak, relatively low field, but MAST is being upgraded, and the version of MAST that will be upgraded is part of this European medium-sized tokamaks circle. In particular, there will be enhancements in the toroidal field, and that will significantly improve the confinement in the central solenoid for increasing the value of the plasma current and the duration of the plasma pulse, and in the plasma shaping capabilities to explore different configurations. There will be an off-axis neutron beam injector so that the control will be of the profile will be possible, and there will be a new innovative configuration for the diverter called Super X for a better power handling. This is a very important exploration, so let's say a few words about that. The Super X diverter is represented here on the left on a short movie that illustrates its functioning. In particular, the Super X diverter leads to longer connection length, and because it takes the plasma from the boundary and brings it basically to a more external chamber at larger values of R, it also lead to a reduced heat flux, because the surface over which the heat is deposited will be larger. The TCV tokamak in Lausanne, Switzerland, where we are, is also part of this medium-sized tokamak group in Europe. And the reason for that is it can provide significant input on the different physics questions, including the question of potential innovative configuration for the diverter problem. The reason why TCV can do that, it is because it has an extreme flexibility in its shape, both in the core and at the edge. The illustrations that are going in front of you here are a proof of that. You can see different shapes that are achieved on TCV, and you can also see a specific shape that's achieved on TCV, which is the so-called snowflake diverter, has been for the first time demonstrated on TCV. Again, it's an innovative configuration for the diverter to improve the question of the heat flux to the diverter target plate, and possibly even the stability with respect to ELMs. TCV is endowed with a very powerful and flexible electron cyclotron heating and current drive system. At the moment, with 6 gyrotrons that work at the second harmonic for a total of 3 megawatts, and 1.5 megawatt total of 3 gyrotrons working at the third harmonic, that is around 118 gigahertz. The flexibility in the system is not only because of the frequency choice between the 2 harmonics, but also because of the possibility of injecting the beams in different parts of the vessel with different angles to both heat the plasma locally, treat instabilities locally, and drive current non-inductively. TCV is also undergoing very major upgrades, both for ion and electron heating. A neutral beam of 1 megawatt and about 30 kilovolt of energy is being installed, and 2 dual frequency gyrotrons of 1 megawatt each at 126 gigahertz corresponding to the third harmonic, or 84 gigahertz corresponding to the second harmonic, are being procured. You see here the different gyrotrons that are installed on the TCV plant, or that will be installed soon on the TCV plant, with the transmission lines that will take the microwave power to the tokamak. Tokamak that will also be heated by a neutron beam injector that's being procured at the moment of about 1 megawatt of power. Naturally, one of the main elements in the European roadmap towards fusion power, perhaps also in the world roadmap, is JET. You can see the JET here appears as major element in the development of the inductive plasma operation. JET is not really foreseen to operate in very advanced modes of operation with a large fraction of current driven non-inductively, but it has to contribute to a number of open issues related to the inductive scenario. JET has a major radius of about 3 meters, minor radius of about 1.25 meters, and the field goes up to almost 4 Tesla with a current up to about 6 megaamperes. JET is devoted at present to really prepare the construction and the operation of ITER, acting as a test bed for the technology and the plasma scenarios that are foreseen for ITER. In particular, JET has an ITER-like wall. It has the same combination of materials as ITER will have, beryllium and tungsten. JET will explore in these ITER-relevant conditions how to prevent or mitigate the edge instabilities we mentioned before. That is, these very short and very violent plasma outbursts that can eject large heat and particle loads on the vessel wall that must be avoided or mitigated for ITER. JET is also a place where there is very large development in remote handling, and this is a technological aspect that is very important for fusion. We need to learn how to operate inside the fusion reactor, which is a hostile nuclear environment for human beings. Finally, JET is the only machine in the world now that can do DT plasmas. And doing DT plasmas implies, of course, preparing directly for ITER operation. Just as an example of the importance of the JET data points for ITER, I show here the figure that we've seen before in the course, the empirical transport scaling that basically has been used for the ITER design. And as discussed before, this scaling is based on a variety of devices. It implies that we can plot the confinement time from the experiment as a function of the confinement time from the scaling law and get a very good correlation. So in other words, the scaling law is representative of the variety of experiments. Now, all of the experiments, apart from JET, are in a relatively far away from ITER region. You can see this is a log-log plot. The points that are by far the closest to that foreseen for ITER are coming from JET. So it's essential to have really the minimum possible extrapolation to ITER in order to be sure or to improve our the reliability of our predictions for ITER, in particular in this case for confinement time. But this is just an example. There are several areas for which such proximity is essential. JET has achieved a triple product of about 2.6 10 to the 20 per cubic meter keV times seconds, close to the record ever achieved anywhere, and it has achieved the record fusion power on Earth with 16 megawatts obtained in the end of 1997 in DT with a fusion gain about 0.6. One point I like to underline in the European roadmap, on which I focus for this lecture, but of course is not the only one in the world, is that even the European roadmap is based on a number of international collaboration. I'd just like to highlight one. This IC stands, in fact, for international collaboration. And this is a picture, which I take here in a simplified and enlarged version, of the Japanese tokamak JT60 super upgrade, which is being completed at the moment, which will contribute very significantly to the R&D needed, in particular for steady state operation of the plasma. This is a superconducting tokamak with about the size of JET, 3 meters major radius, not very different minor radius either, 1.2 meters, up to 2.25 Tesla and up to 5.5 megaampere. So it will really concentrate on the steady-state advanced regimes that JET cannot address. This is an example of complementarity in the world program, in fact, beyond the European frontiers. And now come to what I would say is the main element of the European roadmap, and that is ITER. And you can see that the image of ITER in fact, appears in many different locations here. And that's because ITER is a cornerstone for a variety of the missions we have highlighted before. ITER will be the first burning plasmas. ITER will be the first demonstration of scientific and technological feasibility of fusion and also of its safety. ITER is designed to produce plasmas with a fusion gain of 10 or better. So that's the goal. But that will be done not for small amounts of power. It will be done for a fusion power that should exceed half a gigawatt and for a duration of at least 500 seconds. ITER has a size of about 6 meters major radius, 2 meters minor radius, plasma volume of slightly less than 1,000 cubic meters, toroidal field 5.3 Tesla, and a current flow in the plasma of about 50 megaamperes. Here you can see the construction site for ITER in Cadarache in the south of France, which is in fact evolving every day at present. As you can see, the image of the layout of ITER with a human being represented in the bottom, reminding us of the scale of the project. And just to highlight one of the novelty elements of the ITER plasmas, I have represented here the foreseen Q equals 10 scenario. So that's the one we promised to achieve with 50 megampere, 500 megawatt fusion power. And you see here as a function of the time in the discharge, which lasts 700 seconds, you see the Q fusion gain going up to 10 and then coming back down at the end of the discharge. But the point here that I want to make is that we really have a different regime in ITER compared to what we have in machines today, even on the DDT experiments that we have done in TFTR and JET. Look at the plasma alpha particle power. It's about 1/5 of the total fusion power, so it's about 100 megawatt. And if we take a single shot, one shot of ITER of this kind, we will have an energy in the alphas that will be of the order of 50 gigajoule. This has to be compared with the total energy that we have ever produced in all the DT experiments in the world so far, particularly in JET and TFTR, which is 10 times less. So one single shot of ITER will produce 10 times more alpha particle energy than the whole history of fusion so far. Now, without going to the details of the ITER design, which is extremely complex, as you can imagine, I'd just like to highlight in this picture the main components of ITER. Starting from top here, say this central solenoid. This is the superconducting coil of niobium tin, 6 modules of it. Then we see the vacuum vessel, which is being constructed. It's divided into 9 sectors. A very important piece of the project is the toroidal field coils, represented here in orange. These again are coils made of niobium tin. There are 18 of them. Whereas the poloidal field coils, there are 6 of them, which you see here, a cross section of one. They are in niobium titanium. We can also see the machine supports. And going to the other side, you can see the diverter structure in here. The diverter is made of what's called cassettes, 54 cassettes. These are modular elements that can be replaced over a relatively short time scale. There are cryopumps, 8 cryopumps, very large size. And there are, of course, many openings to access the inside of the tokamak. The example here is that of the iso-rich antenna, which comes on a port plug, as we have discussed in the previous lecture. So 6 of these port plugs are dedicated to heating, 3 are dedicated to the test blanket modules, 2 are for limiters and remote handling, and the others are for diagnostics. The blanket module is shown here as an example. And of course, the whole of the machine is enclosed in what I believe will be the largest cryostat ever built. In this picture, you see the different diagnostic systems foreseen for ITER. Again, we will not go into any details, but you can imagine that the challenges we have for hard plasmas in general are, of course, applicable to ITER, but on top of those, which imply that you cannot put any material surface inside the plasma to measure anything, and that you need to really be clever in interpreting your data from thermal components of the plasma, from non-thermal components of the plasma, etc. In addition to this, we have a hostile nuclear environment that we have not had so far. For example, neutral irradiation. So there's a strong implication of that, for example, on the difficulty of having mirrors in the plasma or close to the plasma for light to be extracted at different wavelength. There's also the question of the feed-throughs for the diagnostic passages that need to be compatible with the machine safety constraints and so on. Here you can see a survey X-ray measurement. You can see ultraviolet of different kinds for spectroscopy, another spectroscopy system for X-rays, reflectometry for the diverter region, Thomson scattering for the diverter region, infrared viewing, electron cyclotron emission for electron temperature, motional Stark effect for having the internal structure of the magnetic field, Thomson scattering more at the edge. There will be Thomson scattering in the core, of course. So a large variety of diagnostics which different partners of ITER are building, all, of course, compatible with the constraints that will be dictated by the machine environment that will be very different from what we are used to today. So there are challenges in building the individual components for ITER, each one being state-of-the-art, each one being subject to a number of constraints, including constraints on availability, maintainability, and durability. But there will also be a major challenge, and that will be to put these pieces together. And what you're seeing here is a movie that represents this assembling of ITER. We say that this is the world's largest puzzle ever constructed. And so it will be quite a challenge to really assemble all of these pieces together in a relatively short time. ITER is not the end of research for fusion. ITER will demonstrate that fusion can be controlled on Earth scientifically and technologically. But we need one step more. We need DEMO. DEMO will demonstrate that fusion energy is also possible commercially. DEMO will need to have a fusion power gain of 30 or a little bit more, with the fusion power of the order of 3 gigawatt corresponding to electrical power of the order of a gigawatt, and will need to work in steady state. And in my opinion, this is sort of a personal opinion, the areas where more innovation is needed are the exhaust of heat from the plasma, the inbreeding of tritium, and the materials. Several concepts are under development in different parts of the world. There's a European concept being developed in Europe, or maybe even two versions of that. There's a concept in Japan, the concept in the US, in Korea, and in China. While I don't want to go into any details for the different concepts, I stress once more that there are elements of competition, which is of course natural, but there are also elements of complementarity among all of these approaches. In summary, we have seen that roadmaps to fusion have been developed in different countries, in different parts of the world. They all recognize the need to develop enabling technology in nuclear environment, something that we have not seen so far. We need to involve industry in the progress towards the demo step, towards a fusion reactor. We need to address materials issues. Materials are a very crucial element of fusion technology. We need to optimize the magnets that will be superconducting for high field. All of these are elements of fusion technology that are absolutely essential. Yet, I believe we can say that plasma physics for fusion is really far from being complete. For example, we don't know how to operate a steady state token like a high field, high density, and high temperature. We have made enormous progress in controlling the plasma and controlling its instabilities, but we don't know yet how to control the fast times entirely, for example. We don't know yet what is the best magnetic configuration at the edge in order to alleviate the problem of the plasma exhaust. These are just examples of plasma physics-related problems that are not fully understood, not fully addressed, and not fully optimized to get as efficiently as possible to the fusion reactor.